Okay, so here's what I'm going to do. Let's write it down as k minus m plus m. And then I'm going to merge the first m terms here corresponding to m with that. That gives me a 1 because this is just the sum of the PDF of the Poisson multiplied by m. So that gives me an m. And then minus summation k from 0 to m of m minus k times e to the power minus m to the power k divided by k factor. And this is actually a funny telescopic sum, if you can see that. This is equal to e to the power minus m times two terms. So the first one, m times this thing. So it is going to be sum k from 0 to m to the power k plus 1 divided by k factorial. And then the second one, k cancels 1k in the k factorial. So you have sum k from 0 to m to the power k divided by k minus 1 factorial. So it's funny telescopic summation. Only one term remains, which is the last term here. So it's going to be e to the power minus m times m to the power m plus 1 divided by m factorial. And merging the two terms, you get just for completeness. So from that calculation, the expected revenue of price P would be equal to n minus this term. If I factor m, so we n times 1 minus e to the power minus m to the power m divided by m factorial times the price. Right. It's actually, to be exact, it is equal to this quantity. If you look at n equal to infinity, for any other n, it is greater or equal to that, but I didn't show it. It uses a stochastic dominance of binomial and Poisson, but I didn't show. Okay, so we're done, right? So expected Poisson from the claim one, we know it is at almost p times m, hence the result. Right. Thanks a lot for your attention. Sorry, I went a little bit over time. But just one last point. You see, as m goes to infinity, this basic converges to 1. And the rate of convergence is 1 minus 1 over square root m type of thing. This is actually information theoretically right. You can make this constant slightly better. There are 2 follow-up papers that they actually try to make this constant better for both iid and non-iid. I have posted the link to those papers on the Canvas site as well, but in the interest of time, we are just going to stick to simpler version. And that's it.
What's the rate for non-iid multi-x?
It's the same thing. It's basically order 1 over square root m, but through a very more complicated argument. That's the magician algorithm that I mentioned at some point. And in my dreams, I wanted to teach it in this course. Yes.
When we want to compare to the optimal method, is this an upper bound on the performance from solving the DP?
DP, what is the DP you are having?
So for example, so
My answer is basically I ask everyone's value and then I do the best.
It's most powerful.
but here you have incentive issues, but for the sequential level, there's no incentive. So if you think about the first case, single
Right,
item,
so you can think of a benchmark which is like the best sequential process pricing, and then you can solve that using DP. I think this is what you're saying. But the best sequential process pricing is not the best option. So optimal market is the best auction, even if you know the entire set of buyers. And even with respect to that, you can become.
But for Mearson, each one knows, I know my competitors. I have the incentive issue there.
Sure.
But for the DP stuff, each one is myopic.
So, I mean, it depends on how you think about the work, right? So basically, maybe the buyers are myopic. But so being myopic is different from being Bayesian. So you might know about the other buyers in the market in the sense that you know their distributions. You just don't know their actual values.
It's one thing Bayesian could do. Bayesian could do say something even better. That's the
Like, but the chance point is that you don't need to be worried about incentives.
Yeah, I also think it's even better. So suppose if you think about the first case, this like users arrive sequentially, I can be adaptive.
in Bayesian can better.
But Mearson, there's incentives there.
This is just one option Bayesian could run, and Bayesian is not optimizing over all the entire space of options in some sense. So it's only sort of.
But if you're restricting your attention to sequential interaction with myopic buyers, then sequential process pricing is best thing you can do. And that you can find using these.
But for example, your first case is a sequential.
But imagine, I'm not making the life of the buyers difficult or easier. I'm just giving more flexibility to the auctioneer. So the auctioneer now can look at the entire pool of the buyers and run a protocol. Even though they are myopic now, they have to think about the entire set of buyers because they know that they compete.
I just consider the first case, like it's not sequential pricing problem.
Right.
There's no incentive at all. Like